Alright, here we are with our video for the basic probability rules. And I know that everybody just loves probability and they really think it rules. So there's several things I want to do in this video, and the first is I actually want to help you with your worksheet that I assigned for homework. So if you actually want to go ahead and pause the video and find that worksheet, we're going to do the very first page. We'll do it together. That way we get this whole front page right for sure. So go ahead, but before I do so, we will get to that first, but I just want to review the rules that we learned real quick in class. And the first rule we learned was the addition rule. Okay, and we talked about in the addition rule, we're talking about one trial. So we're just doing one trial. We're doing one roll of the die, one flip of the coin, one pull of out of the jar of marbles, whatever. And remember, the addition rule, you really have to think, could the two events we're talking about happen at the same time? So we're talking about addition, we're talking about or, okay? We're talking about this or that, A or B. So the probability of A or B, remember that's our U, stands for or, is the probability of A plus the probability of B minus the probability of A and B. Again, this is just back here. This back part is simply because if A and B happen together, meaning not mutually exclusive, then we have to consider the fact that they got counted twice. So we did plenty of examples in class like that. So hopefully you understand that you at least have to think, if A and B could happen at the same time, then I don't want to count them twice. So I have to subtract them away. So that's what you do if you're not mutually exclusive. The second rule we learned was the multiplication rule. And I really want you guys, I'm begging you, to understand that the multiplication rule is really used not when we see the word and, but when we see the word and then, okay, and then. And what I mean by that is we're talking about two or more trials, okay? So we're not talking about necessarily the probability of A and B occurring. I mean, it has a lot to do with that, but I don't want to get you confused, because I'm going to show you later on in this video how you can be confused with that. Just think that, hey, I'm trying to okay, one thing's happening and then another, and then maybe another, and then another, and that's when you have to really think about multiplication, okay? So like, I don't want to really put a formula here. I really don't want to put any kind of formula in here. I just want you to think. But you do have to think about independence. Like we talked about, if you dip into the jar of marbles and you pull out a blue one and then you throw it away, well, when you reach back in, there's now one less marble total. So that changes. So as long as you think about that kind of stuff, the multiplication rule is pretty easy. And the third major thing we talked about was the conditional probability. Okay, we're going to use this a lot in today's video. And the conditional says, what's the probability of A given B has already occurred? So what's the probability of A knowing that B has already occurred? So this formula for this is the probability of A and B. So you just got to think, okay, what's the probability of A and B occurring out of everybody? Divided by the probability of B occurring. Again, that's the probability of B out of everybody. So conditional means there's a condition, like B has occurred. But to find conditional probability, you use these two probabilities, excuse me, which are not conditional. This is the probability of A and B divided by the probability of B. So we're going to do a lot of examples with those today as well. Okay? So first off, let's actually, like I said, if you wanted, pause if you need to, if you have already done it. Go and grab that worksheet, and we're going to do the first problem together. The first problem says we got 5 questions, okay, 5 multiple choice questions, and there's 4 choices each. 4 choices each. So a little bit different than art tests. Art tests usually have 5 choices. But anyway, the first question says you get none of the questions correct. None of the questions correct. So that means that the first one would be wrong. Well, you have a 3 out of 4 chance of getting it wrong. And then you're going to do a second problem. So this is like the multiplication rule. A second thing is occurring, a second problem. And then and 3 out of 4 chance of getting that one wrong. And then a 3 out of 4 chance of getting the third one wrong. And then a 3 out of 4 chance of getting the fourth one wrong. And, so there's 5 questions, so one more here. We got a 3 out of 4 chance of getting that one wrong. So now you could do 0.75. Now I know 3/4 is 0.75 to the 5th power. Okay, if you really want to speed this process up instead of typing it a bunch of times. So the probability here is about 0.2373, and I'd prefer you give me 4 decimals here when you're working with these probabilities. All right. So B So I mean, you think about it, you got 23% chance of getting them all wrong, okay? You get all the questions correct, okay? Well, the probability you get the first one correct is 1/4. Probability you get the second one correct is 1/4. Probability you get the third one correct is 1/4. The fourth one correct, and the fifth one. So that's 0.25 and 5 times. So it's 0.25 raised to the fifth. That is very, very small. Watch out on your calculator screen. You see that e to the -4, so it's 0.00097 66. So very, very small, extremely small probability of getting them all correct. Okay. C says get at least one of the questions wrong. Now I really want you to think what that phrase means. At least one wrong. Now what does that mean? That means you get one wrong, or two wrong, or three wrong, or four wrong, or 5 wrong, okay? That's too many options, okay? And I really want you to understand that one wrong could happen 5 different ways. First one wrong, or the second one wrong, or the third one wrong, or the fourth one wrong, or the fifth one wrong. 2 wrong could happen in, oh boy, a lot of different ways. The first 2 wrong, the last 2 wrong, the first and the third wrong, the first and the third, the fourth, the first and the fifth, the second and the fifth. I mean, there's just so many different options there. So think about what's the one case I didn't mention here. What's the one case? At least one wrong, 2 wrong, 3. The one case I didn't mention is none wrong. So if I do 1 minus the probability of none wrong, I'll have the answer to what I'm looking for. And it's much easier to do one thing than to do all these different things up here, 1 or 2 or 3 or 4 or 5. So I already figured out in the previous problem the probability of none wrong, or all right, obviously. So if I do 1 minus the 0.0009766, or 1 minus 0.25 to the fifth, I get the probability of getting at least one wrong is 0.9990. Extremely, extremely likely that you're going to get one wrong if you're just guessing. So this phrase, at least one, is really, really important that you understand how to do that, okay? D here, get your first incorrect answer on the 4th question. Okay, so the first incorrect is on the 4th question. So that means you got the first one right. 1 out of 4. You got the second one right. 1 out of 4. You got the third one right. Your first incorrect happens on the 4th question. Now, what about the 5th question? What about the 5th question? Well, to be honest with you, the question didn't even mention it. It doesn't matter if I get it right or get it wrong, so I really don't even have to consider it. So my answer would just be 1/4, 0.25 times 0.25 times 0.25 times 0.75. I really don't even have to consider that last question because the problem doesn't hinge on that last question at all. It only hinges on the getting right, and then the 4th one wrong. That's all that matters. So there'd be your answer point, 0117. Now, let's slide over here and let's look at number 2 that we are asked to do on that worksheet as well. Number 2 dealt with the M&Ms, and it says you got 10% that are brown, and you also got 10% that are red. And let's see here, 20% yellow, blue, and orange. So 20% yellow, 20% blue, and 20% orange. The remainder of them are green. So the green would be the remainder. I guess I got to make me do this by hand. So that's 10, 20, 30, 40, 50, 60, 70, 80. 80%, so there's 20% left to be green. Why they didn't just throw the green in with the other 20%, I don't know. Whatever. All right, so the first one says you're picking one peanut butter M&M at random. You're only picking one. So what's the probability it's green? That's easy. 0.2, 20%, that's the probability that you get that one green. Okay, this was little number one, right? Okay, the second one was it is a primary color, red, yellow, or blue. Okay, well, or I got to add red 10%, yellow 20%, and blue 20%. So that'd be 10, 20, and 20 would be 50%, right? Now I do have to think about subtracting. Could they all happen at the same time? No, there's no M&Ms that are red, yellow, and blue, so I don't have to worry about subtracting anything out. All right, and the last question here, for this particular problem was it's not orange. Not orange would be the opposite of orange, or not orange would be 0.80. Not orange would be the opposite of orange. Orange is 20%. The opposite would be 80%. That's easy. Okay, B here said if you pick 4 M&Ms in a row. Oh, now this is the multiplication rule because I'm doing 4 things. I'm picking 1, I'm picking a second, I'm picking a third, I'm picking a fourth. So keep that in mind. They're all blue. All blue. Well, that's 20% for blue. And I need that to happen 4 times in a row. So I can use exponents to start speeding the process up here. So it'd be 20%, 20%, 20%, 20%, or 0.2 raised to the fourth, 0.0016. Now, do I have to consider the fact that if I take a blue one out, is that going to change? Now, nowhere in this problem did it say, hey, you only have 20 candies, and if you take one out and eat it, then they're going to go down. You're going to have 19, and then you eat another one, you're going to have 18. It never said that. They only give me percentages. So I'm assuming that I have so many M&Ms to deal with that taking one away isn't going to matter. Okay? The second question here dealt with none are green. So none are green. So 20% are green. So none are green would be 80%. 80% would be no green. And I need that to happen 4 times. So I need no green, no green, no green, no green. Or 80%, 80%, 80%, 80%. So 0.8 raised to the fourth is 0.4096. Okay? And the third problem here says at least one red. Oh, here we go with this. At least one red. Now that can mean 1 red, or 2 red, or 3 red, or all 4 red. And 1 red can mean the first red, the second red, the third red, and the fourth red. 2 red could be the first 2, the last 2, the first. I mean, too many options. So just think about that. 1 red, or 2 red, or 3 red, or 4 red. The only thing I didn't mention was no red. So if I do 1 minus the probability of no red, I could get my work done in one step. So 1 minus no red. No red would be 0.9, but I need 4 of those. I need no red, no red, no red, no red, because I am picking 4 M&Ms. So I need 1 minus 0.9 to the fourth. 1 minus 0.9 to the fourth is 0.3439. So my answer there would be 0.3439. And, excuse me. The one last question here says the fourth one is the first one that's brown. So the fourth one is the first brown. So that means the first was not brown, 90%. The second was not brown, 90%. The third was not brown, 90%. And the fourth one was the first brown, 10%. So it'd be 0.9 raised to the third times 0.1. And we get 0.0729. 0.0729. Okay? So hopefully that makes sense. So if you need to slow that down, hopefully you guys understand that. The last question says, picking 10 M&Ms in a row, you still have not yet picked a red one. A friend says that you should have a better chance of getting a red one on your next pick since you have yet to see one. Comment on your friend's statement. Now, my friend's statement is stupid because it says that 10% are red, so it doesn't matter that I keep picking M&Ms. Now, if I have a very small bag of M&Ms, it will matter. If I have a very small bag of M&Ms, there's only 1 red in there. Every time I take one out, I have a higher chance of getting that red one. But if I have an enormous batch of M&Ms from the company, which is what this problem seems to be saying, an enormous batch of thousands and thousands of M&Ms, taking 10 out isn't going to even make a dent in that probability. So again, that's where the law of large numbers comes into place, okay? All right, so we did those first page, so hopefully that's a good help for you. Okay, now I want to move on and take a look at this problem. This problem will help you with some later ones on in the worksheet. It says, of drivers stopped, sorry, it says stooped, my fault there, let me go back and fix that. There we go, a little P there. A driver stopped on suspicion of drunk driving. So of all the drivers that get pulled over because police think they're drunk driving, or driving drunk, 78% of them get a breathalyzer test, 36% of them get a blood test, and 22% get both tests. Now I want this to be very clear. Of these 78% that get breath tests, some of them might also get blood tests. Remember, all I know is that 78% get breath tests. It doesn't say only breath test and nothing else. It says breath test. Some of them may get both. Of the 36% that get blood tests, some of them may get the breath test as well. I just know that 36% get blood tests. So the first thing I want to understand here is a lot of kids think that the probability of A and B is just A times B. A times B. A and B is A times B. Not always. I mean, think about this case. Breath and blood. If you would do that, if you would just do 0.78 times 0.36, right? Use your calculator if you need to. I'm going to do it right now. 0.78 times 0.36. 0.78 times 0.36, I do it twice, is 0.2808, okay? 0.2808, which is different than what the problem says. The problem says 22% get both. So what I'm trying to get to is prove to you that just multiplying A times B is not how you do AND, because you have to consider independence. Because obviously, if you get a breath test, that may, and you like pass it, then they may also give you a blood test. So there might be some independence there. Like your breath test result may determine if they also give you a blood test. And you can't just multiply away if they're not independent, okay? So hopefully I just kind of proved that fact to you. So this problem is kind of good if we draw a Venn diagram here. So let's have this circle right here represent getting a breath test. Okay, and there is overlap because it said some people get both tests. Let's have this circle here be blood tests, and I didn't make it bigger on purpose or anything. Okay, now start in the middle. 22% get both tests. Okay, so this part right here, and I'll use red here. This part right here, this part over here that's kind of like this crescent moon, is only breath, not blood. So remember, the entire circle for breath is 0.78. So if I subtract away the 0.22, I get that this circle, this part of the breath circle is 0.56. That is only breath, not blood. So the entire breath circle must add up to the 0.78, okay? Same thing with the blood over here. 36% get a blood test. Well, 22% is already doing for both. So if I do the 0.36 minus 0.22, I get the 0.14. That would be blood test only, not breath. So we got breath tests only, both, blood tests only. Okay, so that would be my OR. Okay, because remember, my OR would be represented by breath, blood, or both. Okay, so on the outside would be people that get nothing, people that got pulled over and got nothing. So that would be 1, take away the 0.22, take away the 0.56, take away the 0.14. So that would be the 8% of people that got pulled over and got neither test. Okay, so hopefully you understand how I got that. I had to think breath only, blood only, and then the both was in the middle, the 0.22. So the 0.08 would be the percentage of people that were left out completely. Okay, so what percent of people get a test? A test means you get a breath test or a blood test or both. That would be the 0.56 plus the 0.22 plus the 0.14, or the 0.92. So 92% of people pulled over get both, okay? Another way of thinking about how to do that problem is, get a test. That means you get a breath or blood. Think about that, breath or blood, right? So you got breath, 0.78, plus blood, 0.36. But remember, we talked about you need to subtract away the overlap. The overlap would be the 0.22. So if I do 0.78 plus 0.36, subtract the overlap, I get 0.92. It's exactly where that 0.92 comes from. So if you've got the Venn diagram, you can get it this way right here. Or if you want to do it the traditional method using the formula, we got breath test, blood test, get rid of both because you don't want that overlap there, because that 22% was counted here because they got the breath test, and here they got the blood test, so you don't want to count them twice, so you have to subtract it. What percent get a blood test or a breath test but not both? So not both. So that would be the 0.56 that gets strictly breath test plus the 0.14 that gets strictly the blood test. So 0.56 plus 0.14, that would be the 0.70, or 70% get blood or breath, not both. So I'm just getting rid of that not both there. All right, what percent get neither? We already kind of figured that out. That's the 8% that would get neither. That's the 8% that would be left out. That's the opposite of OR. So 1 minus the probability of A or B would be neither, okay, because you're getting rid of breath, you're getting rid of blood, you're getting rid of both. So that's the 8% that we got right there. So you could hopefully use that question to help you on some of those other ones from the worksheets, okay? Next up here, I have a question for you. And again, this is a conditional probability question. This is a really good problem. These are very common on the AP test, and I think you'll like this one. It's really not too bad. So a company uses parts from 3 factories, A, B, and C. 30% of its parts come from factory A, 20% from factory B, 50% from factory C, and that should add up to 100% for all the parts, and I believe it does. 2% of parts from factory A are defective. Hold on, we got an announcement here. Hold on a second. Anyway, 7% are from of factory B's parts are defective, 5% from factory C are defective. If a part is found to be defective, so that's your given. That's how I know this is conditional. It's because it was found to be defective. I know the part is defective. What's the probability it came from factory B? All right. The easiest way to solve this problem is what we call a tree diagram. So we start off with parts. Okay, parts can come from factory A. Parts can come from factory B, or parts can come from factory C. Factory A is 30% of parts. Factory B is 20% of parts. Factory C is 50% of parts. Now, if it's from company A, that part could be defective, or it could be okay, or just not defective, right? So it told us that from factory A, 2% are defective, which would lead 98% not defective. From company B, we could be defective or not, meaning it's an okay part. It's a good thing, right? It said from factory B, 7% are defective. So 0.07 would be defective, 0.93 would not be defective. And then from company C, we have 5% are defective. So we got defective and not defective. We got 5% are defective. That would lead 95% to not be defective. So every branch would be an outcome. For example, if I said to you an easy question, if I said, what's the probability that the part is A and defective? Well, it'd be 30% times 2%. You would just follow that branch. So 30%, 0.3 times 2%, 0.02 would be 0.006. So if you would follow that branch would be 0.006. If I said, what's the probability it's from A and not defective? Well, just follow that branch. So it'd be 0.3 times 0.98. That would be did I do that right? Just want to make sure I typed in right. Yeah, 0.294. Okay, and again, you can do this for any of them. So you could do 0.2 times 0.07. Follow that branch for B and defective would be 0.014. B 0.2 and not defective times 0.93, be 0.186. Okay, and then C would be 0.50 times 0.05. That branch would be 0.025. And then finally 0.5 times 0.95. That branch for C and not defective would be 0.475. So you kind of get the idea. Now, what we have to understand here is we know that the chip is not defective. So we're trying to say, what's the probability it came from factory B given it was defective? I mean, we know this chip in our hand is defective. That's a given, okay? So let's use the formula. The formula says it's the probability of B and defective divided by the probability of the condition, which is defective, okay? So probability of B and defective, that's easy. We already know that. Let's follow the branch for probability of B and defective. So here we go. We're going to follow that branch, B and defective. That branch is 0.20 times 0.07, or 0.014. So that's what would go on top. Now the bottom says defective. How many branches? It's not really very specific, just says probably defective. How many branches lead to a defective chip? Well, I see 1, 2, 3 branches lead to a defective chip. So I have to add all those up because, again, I'm using the formula, and the formula says probably defective. 3 chips lead to a defective, or 3 pathways lead to a defective chip. So it'd be 0.006 or plus 0.014. Or, meaning plus, 0.025. It could be any one of those. So my answer would be 0.014. That's the top. That's B and defective. And the bottom would be 0.006 plus 0.014 plus 0.025. Nope, hold on, I messed up. 0.006 plus... I'm terrible using this calculator. 0.014 plus 0.025, and the probability there would be 0.045. Okay, so divide those out, 0.014 divided by 0.045, and we get 0.31 repeating, so 0.3111. So there's about a 31% chance that if we have a defective chip, it came from company B. Why 31%? Well, that's the way the formula worked out. Think about it. Not a whole lot of chips are defective in the first place. But if we know it's defective, look, B has the highest defect rate, 0.07, and B we get 20% chips from, so it ended up being 0.31111, or 31% approximately, all right? So hopefully you understand how that problem was done. And that's a nice tree diagram problem. Usually those kind of problems are pretty easy to work with. All right. Next up here, last problem we're going to work with. Again, we're going to talk about conditional probability, needing to use the formula versus not needing to use the formula, and how you don't necessarily have to use the formula. All right, the first thing here is, what is this? Makes sense. Well, what is this table showing? Well, let's say we went to a college and we looked in a car lot, and we looked at the student lot, we looked at the staff lot, we recorded how many different cars we saw of these different types. So we got Chevys, Toyotas, Ford, and Mercedes. And then we saw if they were from students or they were from the staff. So we have 193 total cars we looked at, 100 student cars, 93 staff cars, and so forth. So I could ask you some real simple probability, like, hey, what's the probability that we found a Chevy? What's the probability that we pick out, of all these people, we get a Chevy owner? Well, there were 88 Chevy owners divided by 193 people. That's easy. What's the probability that we pick a student's car? So what's the probability we pick a random car and it's a student? Well, there were 100 student cars out of 193. That's so easy. I could say, what's the probability that we randomly pick a person who drives a Ford and is a student, right? Pick a person who drives a Ford and is a student. Well, there were 31 cars that were Fords and students out of 193, okay? If it's not conditional, it's always out of the total of 193. But if I said to you, what's the probability that we pick a student out, right? What's the probability of the car being a student given we know it's a Ford? Okay? So given we know it's a Ford, so we have a car, I'm telling you this car is a Ford, what's the probability that it's owned by a student? Well, you would just think, okay, if I know it's a Ford, I'm only allowed to look at the 41 Ford cars. I know it's a Ford. I'm only allowed to look at those 41 cars, 31 of which are students. So there you go, 31 out of 41. Now, I want to show you how we really can use the conditional formula to get the same result. So remember, the conditional formula says, make a fraction, on top goes student and Ford. Student and Ford would be 31 out of 193, because the formula for conditional is not using conditional, so it would be 31 out of the total. On the bottom is the probability of it being a Ford owner. Well, there are 41 Ford owners out of 193, and when we would divide these, the 193s end up canceling because you multiply the reciprocal, hence getting the 31 out of 41. Let's try another one. So if I say, what's the probability that a car, or let's say that I know that I have a staff car. Okay, it's given that the car is owned by a staff member. What's the probability that it is a Mercedes? Okay, well, I say, okay, if I know it's a staff, if it's given it's a staff member, I only have 93 staff members I'm allowed to look at, 20 of which own a Mercedes. So it'd be 20 out of 93. Once again, if you want to use the formula, on top would go Mercedes and staff. Mercedes and staff would be 20 out of 193, again using your totals. On the bottom would be just staff. Well, just staff, there are 93 out of 193 people that are staff. So divide those, the 193s cancel, and you get 20 out of 93. Now, what I like most about this, and I'm going to scroll so that that's the bottom of the screen now, is that for the first time ever, we can actually have a formula that proves independence. Okay? Now, this formula, if you sit back and take about 5-10 minutes to think about it, makes a whole lot of sense. The formula says the probability of A is equal to the probability of A given B. If this is true, if this is a true statement, if the probability of A is equal to the probability of A given B, then that is verifiable proof that A is independent of B. Because this is the probability of A, this is the probability of A given B has occurred. If these are the same, then it proves that B did not impact A at all. Because here, who cares about B? Here, well, B occurred. If these are the same, then it proves that B had no impact on A, thus proving independence. So if I said to you, is the type of car you own independent of being a student or a staff? All you got to do is pick any type of car. You pick it. Let's do Mercedes. Mercedes, right? And then pick a staff or student. Doesn't matter, right? So we'll go student, okay? So I'm going to say, in order for me to prove that the car brand is independent of being a student or staff member, I need to prove that the probability of owning a Mercedes is the same as the probability of owning a Mercedes given I'm a student. Okay? So if being a student affects the probability of me owning a Mercedes, if it does affect it, it's not independence. If these are the same, then it's independence. So the probability of me owning a Mercedes, right? Just a Mercedes. Well, 23 people own a Mercedes out of 193. So 23 out of 193 is 0.1192. Okay, so there's about a 12% chance of somebody owning a Mercedes. However, if I'm a student, then how many students are there? There's only 100 students, and only 3 of them own a Mercedes. So 3 out of 100 is 0.03. So what does this tell me? This tells me that being a student dramatically dropped the percentage or probability of me owning a Mercedes. So this tells me that they are not independent. Independent, okay? Remember, if they're equal, then they are independent. So this just proves that I have a 12% chance of owning a Mercedes. A person has a 12% chance of owning a Mercedes. A student only has a 3% chance. So something about being a student lowered my chance of owning a Mercedes, thus showing that being a student affected my probability of owning a Mercedes. And that is the definition of not independent. Remember, independent says A is not affected by B. A is not affected by B. But I just proved that A, owning a Mercedes, was definitely affected by being a student. So hopefully that will help you as well. All right, guys, good luck on finishing that worksheet. Please, hopefully you watched this video, paid attention, took notes. We will answer any questions you have over that packet on Tuesday when I see you again. All right.